Welcome, everyone. We're going to get started. Thank you very much for joining us today. Before I hand it over to David Murray to get us started on part one of two webinars taking place this week, I wanted to just run through a few housekeeping elements before we get started. So the first is, as I've noted in the chat, we are recording this session. And you'll notice that when you've come on, all participants are automatically muted. We just make sure we do this so that there is clear audio for the recording and for the presenter. There's a few notes on the screen here. If there are any challenges with the audio as you are hearing it now, audio and visuals will come through your computer, so there's no need to dial in. But if there's any issues, there you can download the app, and there's also a help guide as listed on the link here. Also note that Chrome is a recommended browser as well if you're having any challenges. You'll also notice that there is a drop down. If you hover towards the bottom of your screen, there is a few options for you. Importantly is the one icon with the little person, so that you can access the chat. You can feature, the chat is available at any time. You just need to chat me directly and I can answer any questions. And also to note that the consulting engineers attending are going to receive 1 PDH credit for attending this training session. So I am going to put these links in the chat in 1 minute. I'm seeing that question come in. And while I do that, I'm going to hand it over to David and he can get us started.
Thanks, Tanya. Welcome everyone to today's webinar on ground fault protection of solidly grounded low voltage systems, part 1 of 2 fundamentals. On Wednesday, I'll present part 2, which will cover ground fault protection of multiple source solidly grounded low voltage systems. Between the two, there was just too much content to handle in one seminar. I had to break it into 2. By the end of this webinar today, you will learn why ground fault protection is required on solidly grounded 480 volt and 600 volt systems rated 1000 amps or higher. You'll learn about the purposes of grounding and bonding electrical distribution systems, the characteristics of low level arcing ground faults, how ground faults are detected and measured, the ANSIEEE/IEEE numbers for ground fault protection, and we'll have a brief look at ground fault trip curves. I've organized the presentation into 5 topics: arcing ground fault burndowns, a review of grounding and bonding of low voltage electrical systems, phase faults versus ground faults, arcing ground faults, and finally detecting and measuring ground faults so as to protect against them. If we look at the history of low voltage power system grounding, I go back to the 1890s when Nikola Tesla patented his squirrel cage induction motor. Now, low voltage electrical distribution systems were around for 80 years, from 1890 to 1970, before ground fault protection was added to the NEC in the US and the Canadian Electrical Code in Canada. I wanted to know what changed. So the first systems after Nikola Tesla patented the squirrel cage induction motor, the first electrical distribution systems are thought to have been ungrounded delta because only 3 wires were required. In the 1920s, solidly grounded low voltage systems, single phase 12240 or 3-phase 122.8 volt, became popular. Also, later on in the 1940s, corner grounded delta 480 volt and 600 volt systems became popular to solidly ground delta systems. Large delta ungrounded distribution systems are susceptible to damaging line to ground voltage escalation on an intermittent arcing ground fault. solidly grounded 4-wire Y-connected 480/277 volt and 600/347 volt systems became popular in the late 1950s as commercial and industrial building loads grew. These systems could supply 277 volt and 347 volt fluorescent lighting directly without requiring step-down transformers. Today, more than 90% of low voltage power systems are solidly grounded 4-wire. In the 1960s, devastating electrical burndowns made headlines in the popular and technical press. Businessweek had an article from 1964 called "When Protection Does Not Protect." I found a copy of it in a local reference library where I live. The white papers listed studied the problem of low voltage arcing ground faults. They found in these white papers that most arcing ground fault burn downs occurred on solidly grounded 480, 277, and 600, 347 volt distribution systems. The arcing ground fault burn downs were caused by arcing ground faults that had escalated into destructive three-phase arcing faults. Fuses and thermomagnetic circuit breakers did not interrupt the three phases fast enough to protect property and life. And yet, the electrical equipment met the prevailing protection requirements of the Canadian Electrical Code and the National Electrical Code in the US. The trends that led to arcing ground fault burndowns in the 1960s included a gradual change from ungrounded delta-connected 480 and 600 volt systems to solidly grounded Y-connected systems. That meant that ground fault current increased from a few amperes to three-phase fault levels. Early low voltage systems were 208, 120 volt three-phase 4-wire. Increasing load density led to the higher voltage 480 volt and 600 volt Y-connected systems. This increased voltage led to more occurrences of sustained restriking arcing ground faults. And there was a gradual change from lower interrupter ratings like 600 amp to extremely large ratings of 4000 amp. That meant there was much higher available fault current. Finally, economies made fused switches popular, which offer little to no ground fault protection. To protect against arcing ground fault burndowns, ground fault protection equipment supplied by solidly grounded low voltage systems was added to the National Electrical Code in the US in 1971. Here's an excerpt from today's 2020 NEC, section 230.95. Ground fault protection of equipment shall be provided for solidly grounded Y electric services of more than 150 volts to ground for each service disconnect rated 1000 amps or more. Furthermore, the maximum setting of the ground fault protection shall be 12,000 amp with a maximum time delay of 1 second. Ground fault protection of solidly grounded low voltage systems was added to the Canadian Electrical Code in 1972. It is similar to the NEC with the exception that ground fault protection in Canada is also required on 208 120 volt systems rated 2000 amps or more. We will now briefly review grounding and bonding of electrical systems because they play a key role in ground fault protection. There are three concepts I want to touch on: AC system grounding, equipment bonding, and equipment grounding. AC system grounding is the connection of the AC power system to the mass of the Earth, usually from the neutral terminal, as I'm showing here, the secondary Y connected going through a grounding conductor to a grounding electrode. It's connected to the mass of the Earth to provide a reference to ground for the power system, to stabilize the system voltage during normal operation, to limit the voltage rise imposed on the power distribution system during abnormal events such as ground faults, surges, lightning, or unintentional contact with a higher voltage system, and to safeguard against undue voltage stress on the conductor's insulation. The drawing shows the neutral terminal of the Y secondary winding connected to a grounding electrode by a grounding conductor. Equipment bonding consists of the interconnection of conductive materials enclosing electrical conductors and equipment to minimize the possibility of a potential difference between the exposed non-current carrying metal parts. This forms the bonding system. For equipment grounding, that consists of the connection of the bonding system to the mass of the earth at the same location where the AC power system is grounded, so as to provide a low impedance path for ground fault current and to limit the voltage to ground of exposed non-current carrying metal parts. The objectives of equipment grounding and bonding are to provide adequate current carrying capability in the ground fault return path for the duration of the ground fault without creating a fire, to provide a low impedance return path for ground fault current to facilitate the timely operation of the overcurrent protective device, and to reduce electric shock hazard to personnel. This drawing here shows a bolted fault from phase A to the equipment enclosure. The fault then flows through the enclosure up through a bonding jumper to the grounding bus, and then through the bonding conductor upstream to the source, and then through this critical system bonding jumper, which provides the path for the ground fault current to return to the source neutral and complete the circuit. High fault current with the bolted ground fault will quickly trip the circuit breaker. Without this system bonding jumper here, on a ground fault, no ground fault current would flow, and at the point of fault, there would be a shock hazard. The Canadian Electrical Code has a rule for system grounding and AC systems supplied by the supply authority, i.e. for a service entrance, and it has another rule for system grounding of separately derived systems that are not service entrances. Rule 10-210 covers system grounding of service entrances. The ground dead conductor, usually the neutral, must be grounded at the service entrance by the connection to a grounding conductor, and it must be connected to the equipment bonding terminal by a system bonding jumper. There is no mention here of the supply authority's transformer that feeds the service entrance. Mention of it was removed from the 2018 Canadian Electrical Code. However, the utility or the supply authority normally requires the grounded conductor or neutral to be grounded at their transformer. This slide shows system grounding of a service supplied system. The neutral is grounded at the source transformer. Right here you can see the neutral going to the neutral bus, and there's a grounding conductor to the grounding electrode. The neutral is grounded again at the service entrance. So here's the service entrance inside the building. There's the system bonding, there's the grounding conductor, which grounds the neutral bus to a grounding electrode. So this is required by the Canadian Electrical Code. The Canadian Electrical Code requires the neutral to be grounded. Right, let me get that back. The neutral to be grounded at the service entrance, and then the supply authority will usually require the neutral to be also grounded at the transformer. So the neutral will be grounded at 2 points when it's a service supplied system. So there will be 2 system bonding jumpers, here and over here. Now I want to point out one other thing. The grounded conductor that's shown here, also known as the neutral conductor, between the transformer and the main switchboard, the grounded conductor carries both neutral load currents during normal operation, and it carries ground fault current during a ground fault. In effect, the ground-dead conductor functions as both the neutral conductor and the bonding conductor. You cannot run a separate bonding jumper between the transformer and switchboard in service-supplied systems because it would operate in parallel with the neutral conductor, and you cannot parallel a neutral conductor with a conductor of dissimilar size as per Canadian Electrical Code Rule 12-108, conductors in parallel. For a three-phase four-wire load, the neutral conductor is extended to the distribution equipment. This slide shows system grounding of a solidly grounded service entrance system that serves three-phase, three-wire loads. The grounded conductor, which is known as the neutral, is still brought out to the service entrance switchboard so as to be grounded. But in this case, the neutral is not extended to the distribution system. Canadian Electrical Code Rule 10-210 deals with supply authority systems. Rule 212 applies to the AC system grounding of separately derived systems. It requires the grounded conductor to be grounded at one point only, either at the transformer or at the first switch controlling the system. This drawing shows the neutral of a separately derived system being grounded at the transformer. You can see here the neutral bus goes to a grounding electrode through a grounding conductor, and there is a system bonding jumper here. A bonding conductor, sorry, I'm just got to make a point here, because what I wanted to make a point here is that you'll notice there are 5 wires when it's a separately derived system. We have to run a separate bonding conductor from the grounded conductor in separately derived systems. So, and that is because the grounded conductor between the transformer and switchboard serves only as the neutral conductor. A bonding conductor is required to connect the equipment bonding terminals of the transformer and switchboard in order to carry ground fault current to the system bonding jumper and neutral to complete the circuit. This drawing shows the neutral of a separately derived system being grounded instead at the switchboard, not at the transformer. So here's the grounding conductor, and here's the system bonding jumper at the first switch controlling the system. Now between the transformer and main switchboard, the ground-dead conductor carries neutral load currents during normal operation and ground fault current during a ground fault. Still, a separate bonding conductor is required between the transformer and switchboard to interconnect the bonding terminals at both pieces of equipment in order to carry ground fault current from a ground fault in the transformer enclosure, so that can return back to the neutral to complete the circuit and trip the breaker. Now, I just want to note that the equipment bonding system and the equipment and the bonding conductor comprise 50% of the ground fault return path. This path has higher impedance than the phase conductors, from 2 to 6 times higher. The use of a bonding conductor in addition to metallic conduit, where used, is recommended to assure the continuity of the equipment bonding system and to reduce ground fault path impedance. Now we'll compare phase-to-phase faults with ground faults. With phase faults, the fault and I'm showing here an example between a fault between phase A and phase B. The fault return path is through phase or phase and neutral conductors. These conductors have lower impedance and higher capacity than the bonding system. Phase-to-phase faults have higher fault current than phase-to-ground faults. Hence, phase over current devices such as thermomagnetic circuit breakers and fuses provide sufficient protection. Fuses and thermomagnetic circuit breakers, however, cannot distinguish between phase-to-phase faults and ground faults. Now, a ground fault is an unintentional contact between an energized conductor and ground, and by ground I mean the bonding system. Recall that 50% of the fault path consists of the bonding system, which has higher impedance than phase conductors. Ground faults are the most common electrical fault. More than 80% of faults are due to an insulation failure between a phase conductor and ground. And the causes of degradation of the dielectric strength of solid insulation are heat, age, manufacturing defects, mechanical damage. The causes of degradation of dielectric strength of air insulation are moisture and dust. Let's compare bolted faults with arcing faults. Bolted faults actually rarely occur because they're usually caused by human error, not insulation failure. They impose the highest mechanical forces because with high current comes high magnetic fields. They are cleared quickly by fuses or by the short time setting of a circuit breaker trip unit. They cause little damage. Arcing faults are the most common. They normally begin as ground faults. An energized conductor comes into contact with ground through air. The fault can escalate into a destructive three-phase arcing fault as the air between the phases ionizes, and this can result in catastrophic equipment damage, fire, and personnel hazard. Oh, I just want to mention the air gap across which the arc flows presents a resistance to the fault current and further reduces the ground fault magnitude as compared to a bolted fault. The drawings here and in the next two slides are excerpted from J.R. Dunkey-Jacobs' white paper, The Effects of Arcing Ground Faults in Low Voltage System Design, published in the IEEE Transactions on Industry Applications in May-June of 1972. In the upper right-hand corner is the medium voltage transformer rated 1000 kVA with a 480 277 volt Y secondary and a 1600 amp secondary main circuit breaker with long time and short time protection. In this example, the three-phase bolted fault current is 20,000 amps. Sorry, the bolted three-phase fault current is 20,000 amps. The bolted ground fault current is 15,000 amps, and the arcing ground fault current is 7,600 amps. A 480 270 volt system, 277 volt system has an RMS phase to ground voltage of 277 volts, obviously. Ground voltage of 390 volts. In the white papers examining this phenomenon of arcing ground faults, a spark gap was used to simulate an arcing fault. What they found is that 375 volts of peak voltage phase to ground was required to initiate and restrike an arc across the gap. And then once the arc started flowing, the voltage across the gap dropped to 140 volts instantaneous and remained there while the arc flowed. Look at the two voltage and current sine waves on the right. The upper curves represent a bolted ground fault current of 15,000 amps RMS, which is this darker curve here, being driven by the applied 277 volt line to neutral voltage. A fuse or thermomagnetic circuit breaker would clear this bolted fault instantaneously. The lower curves show a restriking non-continuous arcing ground fault with an RMS value of 7,600 amps flowing in pulses, positive and negative pulses. Looking at the voltage waveform right here, when the line to ground voltage of the sine wave rises from 0 up to 375 volts, the arc strikes and the voltage across the arc drops to 140 volts, as is shown right here. The applied voltage, however, is still higher than 140 volts and causes the arcing current to continue to rise. So the arc strikes and the current continues to rise while the applied voltage is higher than the 140 volts across the arc. Once the applied voltage waveform drops down to 140 volts, the arcing current stops rising further. And you can see that happening here. The arcing current stops rising and then starts to drop as the voltage, applied voltage drops. Once the arc hits zero current, the pulse stops conducting and the arc is quenched. During the next half cycle of the negative voltage waveform, the cycle is repeated but on the negative side and another pulse of current is created. The result is a series of restriking pulses of arcing current, a sustained arcing fault. The energy of the recurrent arc releases tremendous heat in an extremely short time. The surrounding air heats up, pressure builds, doors blow open, and copper is melted in seconds or less. It was found that the arcing ground fault current could be as low as 38% of the three-phase bolted fault current in 480 volt systems. Grounding and bonding system impedance further reduced the arcing ground fault current level. Donkey Jacobs' 1972 article concluded that arcing ground faults should be cleared within 6 to 12 cycles or 100 to 200 milliseconds to minimize damage. Let's look at how the phase over current devices react to arcing ground fault currents. These are the tools that coordination engineers had back in the day. Here we have a 1600 amp circuit breaker with long time and short time protection. The arcing ground fault current is 7600 amps, which is right here, IGA, arcing ground fault current. Bolted ground fault current here is 15,000 amps, and there's the three-phase bolted fault current, 20,000 amps. Looking at the time current trip curve, if the short time curve were set at 5 times pickup, it would fail to pick up the arcing ground fault current in this example. It would be the long time curve that would pick up and trip after 5 seconds, which is obviously too long. The short time pickup setting would have to be set as low as 3 times to pick up the fault and trip within 200 milliseconds. There's the, on the time current curve, 12 cycles or 200 milliseconds is when the short time curve would trip. Phase over current devices may not sense arcing ground fault currents quickly enough, particularly on upstream main and feeder breakers, where the short time pickup setting is typically too high to detect arcing ground faults, and the long time setting takes too much time to interrupt arcing ground faults. Arcing ground fault burndowns occurred more frequently in the 1960s as phase to neutral voltages increased from 120 volts to 277 and 347 volts, leading to an increased probability of recurrent restriking arcing arcs during ground fault. Main services grew larger than 1,000 amps, which caused higher available fault current and more damage. As a result, the NEC and the CEC were amended to require ground fault protection on 480, 277, and 600 347 volt Y systems solidly grounded rated 1,000 amps or more. That's where the risk was, and that's why the threshold of requiring ground fault protection starts at 1,000 amps. Now we'll look at how to detect, measure, and protect against ground faults. Phase over current protection protects phase conductors. Ground fault protection protects the bonding system from overheating and damage. Ground fault protection is intended to minimize and, as far as possible, eliminate equipment damage and fire hazards relating to arcing ground faults. Ground fault relays sense only ground fault current. They're insensitive to phase-to-phase faults and overloads. Hence, they can have lower pickup settings than phase over current devices. This allows phase over current protection settings of the mains and feeders to be optimized for coordination and to prevent nuisance tripping. So how is ground fault current measured? Well, from first principles, 3 sine waves of equal amplitude, phase shifted by 120 degrees, always sum to 0. An example is a balanced 3-phase load. I took 2 points on the curve, one at 45 degrees and another at 270 degrees, and sure enough, the math in both cases sums up to 0. So the sum of the 3 instantaneous points is always 0 at any point along this graph. Furthermore, 2 sine waves of equal amplitude, phase shifted by 180 degrees, always sum to 0. That's probably more obvious on this curve, 2 curves here. And an example would be a single phase load, be it phase to neutral or phase to phase. So let's look at an unbalanced load. It consists of a 3-phase balanced load plus a single phase load. Each of those 2 components by themselves sum to 0. So the currents in A, B, C, and neutral sum to 0. A ground fault is like a single phase load in that fault current goes out on one phase and returns in the bonding conductor. That's what I'm showing here. A fault phase A to the enclosure, closure through the bonding jumper to the ground bus, flows through the bonding conductor upstream through the system bonding jumper, returns to the source. The sum of the phase A current going out on phase A and the current returning back in the bonding conductor is 0 because they're equal and opposite. But there is no CT on the bonding conductor to cancel out the current measured on phase A. In the absence of any other load, a CT on phase A would measure the ground fault current in this example. Imagine 3 loads, a balanced 3-phase load, a single phase load, in this case I'm showing from phase C to neutral, and a ground fault, which I'm showing from phase C to the bonding conductor. Notice that the CTs on phase A, B, C, and neutral have their secondary windings summed together. So they're connected in parallel so that they're summed together. We know that the sum of the balanced 3-phase loads between these CTs will be 0. We know that the sum of the single phase load between phase C and the neutral will be 0. The remaining phase C current does not sum to 0 because there's no CT on the bonding conductor to cancel out the ground fault current on phase C. The remaining current, or residual current, when the secondary windings of all 4 CTs are summed together in parallel, is the ground fault current. So what flows through the relay here is a residual current from the secondaries, and that residual current represents the ground fault current. It's proportional to the ground fault current because it's divided by the CT turns ratio. So ground fault current divided by the CT turns ratio is the residual current coming out of these CTs. Kirchhoff's current law also shows that the ground fault current equals the sum of the phase and neutral currents. The sum of the currents flowing towards the node in the network is equal to the sum of the currents flowing away from a node. Residually connected current transformers are the most common method for sensing ground fault current. In electronic trip molded case circuit breakers, such as shown here, the phase CTs A, B, and C are embedded in the 3-pole circuit breaker as shown. For 4-wire loads, a separate neutral current sensor external to the breaker is provided. Depending on the circuit breaker rating, ground fault current pickup range can be from as low as 20 amps to as high as 1200 amps. 1200 amps being the maximum pickup setting for normal operation in the Canadian Electrical Code and the US NEC. Ground fault current can also be measured with a zero sequence current sensor. It is another form of residual sensing of the phase and neutral conductors, and here's how that works. Remember that current flowing through a conductor produces a magnetic field that encircles the conductor. The magnitude and direction of the magnetic field is proportional to the magnitude and direction of the current. Now, if I can sum up the phase and neutral currents to obtain ground fault current, then so can I sum up the magnetic fields around the phase and neutral conductors to also derive ground fault current. If the magnetic fields sum to zero, that is, they cancel each other out, then the ground fault current is zero. If the magnetic fields do not sum to zero, that is, there is a residual magnetic field, then that magnetic field strength and direction will be proportional to the ground fault current. In a zero sequence current sensor, the phase and neutral cables are bundled together and run through the center of the current sensor window. Just as shown here. Any residual magnetic field from the conductors will be captured in the iron core of the current sensor. The current in the secondary windings, or the secondary winding, of the zero sequence current sensor will be proportional to the ground fault current. Zero sequence current sensors can be made very sensitive. They are used in ground fault circuit interrupters to sense 5 milliamps of ground fault current, as is shown in this 120 240 volt 3-wire single phase ground fault circuit interrupter circuit breaker shown here in the drawing. And inside the circuit breaker indeed is a zero sequence CT. That's why these breakers have pigtails, because unlike a normal breaker where you can just bring the load neutral to the solid neutral bus bar, we have to bring the load neutral to the breaker so that it's run through the zero sequence CT, and from the breaker is a pigtail to the solid neutral, or you can use the new plug-on neutral breakers to eliminate the pigtail. Zero sequence current sensors are also used in high resistance grounded systems to detect feeder ground fault current, where the ground fault current is typically limited to 5 amps through a neutral grounding resistor. And 5 amps is too low of a current to be detected by the residually connected CTs of electronic trip circuit breakers with ground fault protection. Ground source return current sensing is another method for measuring ground fault current. We directly sense the ground fault current returning through the system bonding jumper using a current sensor right here. So here's the system bonding jumper and a current sensor on the system bonding jumper. This method does measure the ground fault current, but really only for the main device. This method doesn't provide the ground fault current measurement of any downstream feeders. But if you just need the mains ground fault current measurement, this is another way to do it, aside from residually connected current transformers in the breaker, the main breaker. Here are the ANSIEEE IEEE trip numbers that you often see on drawings. The number 50 represents instantaneous phase over current trip. The number 51 represents a time over current trip of phase currents. An N suffix means residually connected current sensors, or a zero sequence current sensor, are used to measure ground fault current. A G suffix means ground source return sensing is being used to measure ground fault current. The absence of a suffix means it is a phase over current protection function. The presence of an N or an G suffix means it is ground fault protection. 51N is the most commonly used method of detecting ground faults. A time over current trip curve with adjustable time delay on pickup, so you can have coordinated ground fault breakers, using residually connected current sensors embedded in the LSIG circuit breaker to measure ground fault current. This slide compares ground fault and short time pickup settings. The ground fault pickup settings are here as a multiplier of the current sensor of the breaker. So I ground fault equals IN, the current sensor rating of the breaker, times 0.2 to 1.0. So in this particular case, for a breaker between 400 amps and 1200 amps. So 1200 amps is a 1.0 multiplier because 1200 amps is what the code says is the maximum ground fault current pickup in most applications. Whereas you can see the short time protection, which they had to use in the 1960s and earlier, the lowest setting was 1.5 typically to as high as 10, and so the takeaway from this is that obviously ground fault current pickup can be made much more sensitive to capture those arcing ground faults. Now, I just want to show you the ground fault protection settings on a typical electronic trip breaker. There will be the pickup setting, IG, and a time delay setting. So the pickup settings are, as we just discussed, a multiplier of the current sensor rating of the breaker. And the time delay settings are no intentional delay, or 100 milliseconds, 200 milliseconds, 300 milliseconds to 400 milliseconds. So coordination intervals of coordination time delay intervals of 100 seconds between successive levels in a distribution system. So there's two sets of curves here, I squared T off in the black and I squared T on in the white. I squared T on provides an inverse time current curve portion, and this helps a coordination engineer to better coordinate with downstream fuses, because fuses have an inverse time current characteristic to follow I squared T. If this breaker is being coordinated with downstream or upstream circuit breakers have a definite minimum time trip L-shaped curve. So that's I squared T off, and it just makes it easier to coordinate with downstream breakers. Here's a typical ground fault protection curve showing, well, here's the I squared T on inverse time current curves. If I squared T off, they'll just be a straight L-shaped curve, and then you can have different time delays from no intentional delay, which is 80 milliseconds, to up to 400 milliseconds of added delay. So to summarize, I hope I've met the objectives set out at the beginning of this webinar. Ground fault protection distinguishes between ground faults and phase-to-phase faults because the current sensing methods for ground fault protection filter out or ignore phase-to-phase faults. The three methods are residually connected current sensors, ground source return current sensing, and a zero sequence current sensor. Hence, ground fault pickup settings can be made low enough to detect arcing ground faults. And ground fault protection is required on solidly grounded 480, 277 volt or 600, 347 volt Y services rated 1000 amps or more, because that line to ground voltage can sustain arcing ground faults, and services 1000 amp and higher have enough available fault current to cause severe damage if not protected from arcing ground faults. Well, that's the end of part one of this webinar.
Thank you, David.
Thank you, Tanya.
All right, so we're going to move over to some Q&A, but before, so as I mentioned earlier, as part of housekeeping, the chat is where we're asking you to submit any questions. So if you can go ahead and do that, I already have one coming in, which I will read out in a moment. Before we do that, though, I'm hoping we can just go to the next slide. There's a few additional things just to give everyone a chance to enter their questions. If you could scroll to the next slide, David, please.
Sorry, yes.
Yeah, no worries. So just to answer the question we get is that would definitely a recording of this webinar will be, and all webinars will be uploaded we're aiming within the next 5 business days or the next week. It will be on the same webinar page you registered for the series. So that will be available, and please reach out to us if you have any other questions. There's some contact information through email. And in the chat, which I've done right now for everyone, I'm putting some of these links. So you can register now, and I'm going to go through a few slides to talk about our Consulting Engineer Partner Portal, and there's a link there to register once we go through it. There's also additional webinars. So again, part 2 of David's webinar today will be on Wednesday, so please be sure to go to this link in that same page and to register. And also there's technical support available through or any questions through the 1-800 number. And again, from a training credit standpoint, all consulting engineers are going to receive the PDH credit for attending this training session. And you will have be able to view that certificate in the My Learning link shortly when it is available. So if you I'm seeing a couple questions come in, so keep them coming. If you could just click on the next couple slides, I'm just going to quickly run through the partner portal. We have consolidated and organized all relevant consultant information in our PRM portal. If you click on the next slide, you'll see here we're just highlighting some of the quick links, actually the one above, where you will see a library of webinars, spec templates, white papers. And if you click on the next slide, you'll also see that all upcoming specifier related and PDH eligible webinars and events, they'll be right on the homepage there. You click on the next one. Also, Layout Fast is also available on the portal, and that allows you to import our accurately sized Schneider product models with the electrical data already configured or pre-configured into Revit. And then also our portal has design tools such as selective coordination, as well as an arc flash analysis tool. So if you go to the Schneider Canada homepage, you'll see the login in the top right-hand corner. And if you click on the next slide, it's very simple, just email and a password, and you are good to go. So the next slide, I've put that link in at the bottom of the links I did provide. We do very much appreciate any feedback you can provide. There's the QR code, but we've also included the link, which will allow you to take just a few minutes, give us some feedback, and allows us to ensure we're delivering great content for you. So let's go through some of these questions, David, that are coming through. Just give me a second. There was one earlier on. Okay. Okay, here's one. Do the breakers with LSIG have zero sequence CT, or is it residually connected CT?
The circuit breakers without LSIG, without ground fault protection, would not have the feature of ground fault protection at all. Circuit breakers with LSIG would have normally embedded internal CTs that are residually connected. It is possible to have an external ground fault relay using either separate external residually connected CTs, or the ground fault relay could work with a zero sequence current sensor as well, and then it would shunt trip the breaker on ground fault. But typically, you know, you can just get that all built into one breaker today without having requiring a separate ground fault relay. That answers your question.
Thank you. An earlier question came in, what is a separately derived AC system?
It's a system which has an isolation transformer where the primary and secondary are isolated from each other, and the secondary forms a new isolated power supply that has to be, well, that for a solidly grounded system has to be grounded. So the grounding system is isolated from the primary through an isolation transformer. And that is, or it could be a generator as well. A generator develops a new three-phase power source that with a neutral that typically is grounded, and that forms a separately derived system also. It's to distinguish it from a transformer, an isolation transformer that is supplied by the utility.
Okay. Another question, how come the 120, 208 volt systems are not focused for ground fault protection? What is the best strategy for GF on over 1000 ACE systems?
Okay, that's a good question. So 208 volt systems, the phase to neutral voltage is 120 volts, and they typically, it's harder to develop restriking arcing ground faults on 120 volts. You know, the testing that was done and the modeling that was done in the 60s in that paper showed that it was much easier to develop recurrent restriking arcing ground faults when the voltage was higher, because it required 275 volts of peak voltage to ground to spark the arc gap. However, that said, 208 volt arcing ground faults are not unheard of. So the CSA has made it that, hey, if you have 2,000 amps or more available, there's enough available fault current there that if an arcing ground fault were to happen on a 208 volt system, they want to see protection. And the U.S. thinking is different, and their focus is on just ground fault protection on the higher voltage systems, 1,000 amps and higher. As far as the strategy for ground fault protection, the code is a minimum safety standard. There's no reason why you couldn't have ground fault protection, for example, on an 800 volt system or 800 amp system, pardon me. But for ground fault protection on 1,000 amps and higher, like let's say you had a 4,000 amp main switchboard feeding some power panel boards, feeding some downstream branch panels. You may want to have ground fault protection. The code just says you need ground fault protection on the main breaker of the 4,000 amp switchboard. But if you had a ground fault somewhere in the system, I mean, the code is concerned about safety, not so much power outage or safety. You may want to also have ground fault protection on the feeders of that main switchboard, so that a ground fault protection takes out just a feeder and not the main breaker. So for a strategy, it's often a good idea to have 2 or more levels of coordinated ground fault protection. It just depends on how critical the load is, or you know, how essential the load is. In the U.S., for example, just as a side note, Article 517 which is for healthcare facilities in the National Electrical Code, actually requires ground fault protection, a second level of ground fault protection on the feeders and one on the main. In Canada, that's done at the discretion of the consulting engineer and designing the system. But it's very common to see coordinated ground fault protection.
Okay, another question. When do you need to have a 4-pole ATS?
That's a good question, and that will be answered in spades on Wednesday, but I'll give you a sneak peek. Because when you have an automatic transfer switch, you have 2 sources, and so that's what I'm dealing with on my Wednesday seminars. How do you deal with multiple source systems and ground fault protection? But bottom line, when the generator has ground fault protection on it, so when the generator breaker is rated 1,000 amps or more, or can be adjusted to 1,000 amps or higher, then that generator breaker needs ground fault protection. And as soon as the generator breaker needs ground fault protection, the generator and the utility main should both be separately grounded, and then the neutral needs to be switched. If the system is 800 amp or less, the generator system, then a 3-pole ATS can work with a solid neutral terminal that interconnects the neutral of the generator to the neutral of the utility source, and that neutral will be grounded back at the utility source at one point only. That works. But as soon as you have ground fault protection or multiple ATSs in the or ground fault protection in the generator, it's a lot easier to do ground fault to make the ground fault scheme work if you have a 4-pole ATS.
Okay, we have time for one more that's just come in. If a building has several service entrances, do the service grounds need to be connected together?
Yeah, that's a good question. It's not that the service grounds, it's the code has a requirement about if a facility has multiple grounding electrodes, you need to bond the electrodes, the grounding electrodes together with a grounding conductor. So I think that's where you would find having to interconnect the grounds would be between the grounding electrodes. And sometimes the service entrances can come in and go to just a common grounding electrode.
Okay. Another one, I think we have time for that. Do you switch neutral, and how does that relate with closed transition ATS?
So you can have a closed transition ATS with an unswitched neutral if the system doesn't have ground fault protection in the generator breaker. But if you have ground fault protection, whether it's closed transition or open transition, you need to have a switch neutral to prevent parallel paths for the neutral current to flow and ground fault currents to flow. So with closed transition, a 3-pole ATS can work, but it has to be one where you don't have ground fault protection on the generator.
Okay. I have one more. Let's squeak. This will be the last question. In Canada, I just see the downside of transformer and service panel grounded separately. I wonder, what is the minimum requirement on ground resistance? Does it impact ground sensor selection? And this will be our last question.
No, no. The resistance of the earth itself, to ground, if that's what your question is related to, the resistance of the earth between the grounding electrode and earth, it doesn't impact the sensing or sensitivity of the ground current sensors because they're responding to the ground fault current that's flowing in the bonding system. Ground fault current at low voltage doesn't flow in the dirt because the resistance of earth is just so high at low voltage that we're just limiting the ground fault current to the bonding system. And there the currents are high enough that the CTs are more than sensitive enough to detect that.
Okay. Well, thank you. Well, the good news is we know you'll be back on Wednesday, same time for part 2. So if there's any other questions we didn't get to, please register for Wednesday's session, and David will be available for questions going forward. Thank you very much, David. Is there anything you wanted to close with before we close this up?
Yeah, I just wanted to thank everybody for joining. I love the questions. Thank you so much. And I look forward to hopefully many of you attending part 2 on Wednesday. Thanks again.
Excellent, thank you. And I just want to note to a few of you who were asking again that with respect to the recording, it will be available within a week back at the same page you registered. And with respect to the credits available, it's on the My Learning page, but I am taking these questions back and I'll find further direction for you. For those of you, I have your name, just a note, and we'll get back to you with some of those answers. So thank you, everyone. I'm going to close off the webinar now, and hopefully we will see you all on Wednesday. Thank you, David.
Thank you, Tanya. Thank you, everybody.